This lesson on common logarithms reviews what was covered in the previous lesson on 10.4a, going over the change of base formula again, and going through a couple more examples of solving logarithmic equations or exponential equations using common logarithms, and then it wraps up this lesson with an application. So as you can see here, the common logarithm again is log base 10, and the subscripted base is implied. Now the change of base formula rewrites a logarithm of any base as the ratio of two common logarithms. Now it could go to any base really, but we use the common log because that's what the calculators are programmed as. So in the first example, use a calculator to evaluate each expression to 4 decimal places. The number that is visibly higher, the 4, that will go into the common log into the numerator, and we'll divide that by the common log of the number that is visibly lower, the subscripted 7. Put that into a calculator using the approximation symbol, rounding to 4 decimal places, you get 0.7124. For the next example, I know the base of 5 is greater than 1/9. That's not what I mean by visibly higher. Instead, the 1/9 is going to go into the numerator, into the common log. We will divide that then by the common log of the subscripted base of 5. Make sure to use parentheses here, and before hitting divide for the common log, and rounding to 4 decimal places in the calculator, we get our answer of negative 1.3652. So that's a quick review of the change of base formula. Next, we'll continue practicing using common logarithms to solve exponential equations. Those are the ones with the variables and the exponents. So as you can see here in these 3 steps, you first take the common log of both sides of the equation. What you do to one side, you could do to the other. That's a long-standing property of equality. Then, here's the money step. We will use the power property of logarithms to multiply the exponent by the logarithm. Remember, exponentiation goes to multiplication. If you raise an exponent to an exponent, it's the same as multiplying those exponents together. And then we'll solve using algebraic techniques. So here we have a variable in the exponent, and so I could take the common log of both sides because the logarithm has that power property that allows you to move the exponent down in front as a multiplication. Use parentheses when bringing down that exponent. There's more than one term there. That will then be multiplied by the common log of 5. And so now we have, oh wait, let me think about that. If my goal is to get w by itself, and there's only one copy of that w, then really I'll just go ahead and divide the common log of 5 to the other side. I want to isolate that w. So these divide out, and now I have w plus 3 is equal to the ratio, the common log of 17 on the common log of 5. Now technically you could put that into the calculator right now, but then you'll be rounding, and then really you just, and you'll be rounding before the last step, so hold that thought, subtract the 3 from both sides. And this is what you'll put into the calculator, and rounding to 4 decimal places, you arrive at your answer. W is approximately equal to negative 1.2396. So in review of this problem, because the variable's in the exponent, we need the common logarithm, because that allows you to move exponents down into multiplication spots. Now let me just throw this out there. Because this is very typical exponential equation, b raised to a variable exponent is equal to some result, you could apply the definition of logarithms right away and go log base b, and then because logarithms are inverses of exponential equations, swap the input with the output, domain and range, the x and the y, log base b of y equals x. So let's see if we use that strategy, what would happen. I'm going to do that over on the side, and so I get log base 5 of swap exponent with the result. So now log base 5 of 17 equals w plus 3. Notice that brings us kind of right around here, but we'll need to use the change of base formula on the log base 5 of 17. So I could rewrite that as the common log of 17 over the common log of 5 is equal to w plus 3. And then you subtract that 3 over and you're going to get to your answer. Now, as I mentioned in the 10.4 part A lesson, in that note sheet, this strategy here that I used on the side doesn't generalize well. So let's take a look at the next example, and if I try to do that here, what's going to happen? So instead we could take the common log of both sides, and then we could proceed by taking the exponent down in front. Now let me pause here for a second. You can use that other strategy where you take this exponential equation and write it into exponential form. So into logarithmic form. Right now we have b to the x is equal to y. So it would look like this. If you could follow it, that's pretty good, but the base will be 2, and now you swap all of this. So then it's going to be 5 raised to 2n minus 1 is equal to n plus 1. I just personally think that's a lot harder to keep track of. But as you can see, then you'll still be able to move that exponent out front. And then eventually you'll need the change of base formula. So I'll go ahead and apply that now. So it's calculator ready. And then really I just need to get that n by itself, so divide that to the other side, divide by fraction, multiply by the reciprocal. I don't know. I don't think that strategy is better, especially when it comes to this kind of problem. So I'm going to go ahead and erase that. And continuing with taking the common log of both sides, I now move the exponent out front. Using parentheses because there is more than one term in the exponent. And so here everything is on the same level. Now I need to get the n's on one side of the equation. So I will have to distribute through, in this case, so then I could dissolve the parentheses out of the problem. And now I can move all the terms without n to the left and all the terms with n to the right. So I'll get the common log of 2 plus the common log of 5, and that's going to equal 2n times the common log of 5 minus n times the common log of 2. You could rewrite this as the common log of 2 times 5, which is 10, just so it's one term, or you could keep it as 2, your choice. Over here on the right hand side we have a GCF of n, so we will factor that out front. And now that's really just all one number. And you could do logarithm properties, you could tuck that away, so that'll be the common log of 5 squared, which is 25, and then you're subtracting the common log of 2 from that, and then you could do the quotient property and rewrite that as the common log of 25 on 2. You could do those kinds of things if it helps you proceed with the algebra of getting n by itself. I'm really just going to take all of this and divide it to the other side. So I'll get the common log of 10 all over 2 times the common log of 5 minus the common log of 2. That will equal n. Now when you put it in the calculator, make sure to put the whole denominator in parentheses. The division operator is a grouping symbol. And if you don't put the parentheses around the denominator, the calculator will not treat it as an entire group. So the final answer, approximating to 4 decimal places for n, we have 0.9117. In the next example, we have an exponential inequality. So if you were to do the definition of logarithms, log base 2, and then swap the input with the output, 7.31, and then b plus 1 here, b is now on the other side with respect to the inequality, so you'd have to change the direction of the inequality. I don't like using that strategy. Instead, I'm just going to take the common log of both sides. And this strategy generalizes well to later on in the chapter when we get to solving natural logarithmic equations. So there's going to be a different base, not base 10, or these real number bases, not real number, but like these integer bases and rational bases will work with Euler's number E, and will be taking a natural log of both sides. But that's getting ahead of myself here, so getting back to this problem, I was just trying to emphasize that the strategy that we're using here works really well with really all types of problems involving variable exponents. So you learn this one strategy and it carries you all the way. So I want to get b by itself. I only got one copy of it, so I will divide that log of 2 to the other side. Now, here's the issue with this. The common log of 2, is that a negative number? We should ask ourselves that because we are working with an inequality, and if you multiply or divide by negative, you have to change its direction. Well, let's think about the following example. If we have log base 8 of 2, the answer is 1/3 because I'm asking 8 to what power is equal to 2, and the 1/3 is the same as the cube root of 8. Well, 1/3 is greater than 0, so we do not have to change the direction of the inequality. We are not dividing by a negative. What it would look like if we were, it would be like the common log of a fraction, let's say 1/10. Because now we're asking ourselves, what do you do to get from the base of 10 to 1/10? Well, that's when you need negative exponents to get that reciprocation going. Alright, so now we just subtract 1. Go to the calculator. Rounding to 4 decimal places, we arrive at approximately 1.8699. B is less than or equal to that value. Now it's time to apply logarithms. This is involving earthquakes. So the amount of energy E in ergs, it's a unit of energy, that an earthquake releases. So that's when tectonic plates slip against one another. So these are massive objects, so massive amounts of energy can be released. So because these numbers are very large, logarithms will help us to understand them with our small, like our brains, which don't understand very large numbers very well. So logarithms help you focus just on the exponent in the problem, usually the smaller number, and then really have an understanding. Like pH, it's on a scale from 1 to 14, but it measures things that are really small, like hydrogen ion concentrations like 0.000095, and but then if I just tell you the number like 5, then you can interpret that very nicely as weak acid. So we have this Richter scale. Sometimes it's still used. There may be like a new formula that describes the energy released, but we're going to go with the Richter scale because that's the familiar one here, and it goes by magnitude m. Here's the equation. The common logarithm of the amount of energy in the system in ergs equals 11.8, some constant. Kind of think about that as a y-intercept. It's a constant in the problem, plus 1.5 capital M. Now that's like the magnitude, so like a 5. You'll hear that on the news, etc. So an increase in 1 step on this logarithmic scale, like going from pH of a 6 to a 7 goes from a weak acid to neutral, like water is a 7, mineral water, corresponds to a 10 raised to the 1.5 power, which is about 32 times increase in the amount of energy released. So, like, between a earthquake of magnitude 7 versus of magnitude 8, you're talking 32 times increase. That's a lot every time you step up on the scale. So an increase of 2 steps corresponds to, well, 10 raised to the third, or 1,000 time increase. So that corrects what I just said. So it grows exponentially. Like, it's a lot of energy, and you can check that out on wikipedia.com for more information. So in Haiti, that devastating earthquake of 2010 measured a 7 on the Richter scale. All right, we got to have a feeling here that this is going to be massive. Let's find out how much energy this earthquake released based on this Richter scale, which uses logarithms. So we go in and we rewrite the formula just to get our bearings here. The common log of energy equals 11.8 plus 1.5. Now, it's not million for capital M. That is magnitude M. And let's go ahead and substitute in. Now, we're going to solve for E. Right now, it's inside of a logarithm. Keep that in mind. But we have the M in this context is equal to 7. So let's clean up the right-hand side here. Let's see here. 1.5 times 7. Well, that's 7 plus half of 7, or 3.5. So we're looking at 10.5, which will now add to 11.8. All right, to get E by itself, and no longer as the input of the common logarithm, we understand that the common logarithm is base 10. So if it helps to actually write that in, so then you kind of have a target. So that is the base, and then you swap the input with the output because of the inverse nature of logarithms with respect to exponential equations. All right, so amount of energy is equal to 10 raised to the 22.3 power. Let's kind of put that into perspective. So E will be approximately equal 1.995 times 10 to the 22nd power, approximately. And let's put this into a perspective. A billion is a 1 with 9 zeros after it. And this is times 10 to the 22nd. And a trillion is equal to 1 times 10 to the, see if a billion has 9, then this has 12 zeros behind it. So this is almost like, so basically, I mean, this is the answer in ergs. Go ahead and box that. But just to kind of wrap our minds around this, which really is next to impossible, you have the amount of energy is a trillion ergs, because you have the Earth's crust, this massive object, creating all this friction from shifting. And definitely check out the corresponding science to really understand what's going on there. But this leveled, like, the Haiti completely. Lots of energy here, and this wraps up the application of common logarithms.